All right, this is section 1.3, evaluating limits analytically. So we'll start off with a few properties of limits. First of all, we have direct substitution. That's when you can just substitute c for x if the limit as x approaches c of f of x equals f of c. Just plug in the value anytime you can. That only works if the function is continuous at c. That means the function's limit can be evaluated with direct substitution. Theorem 1.1 are some basic limits. If b and c are real numbers and n is a positive integer, the limit as x approaches c of b, so just some constant, is b. The limit as x approaches c of x is just c. And the limit as x approaches c of x to the n is c to the n. Let's look at what that looks like. So the limit as x approaches 2 of 3. Well, that function's always 3, so the limit is also 3. The limit as x approaches negative 4 of x, well, that's just negative 4. I just plug in my x value. And the limit as x approaches 2 of x squared, I plug in the 2 for x, giving me 2 squared, which is actually 4. Then we have some properties of limits. So b and c are real numbers and n is a positive integer. Let f and g be functions with the limits the limit as x approaches c of f of x equals L, and the limit as x approaches c of g of x equals K. Scalar multiple limits work the same way. The limit as x approaches c of some constant b times f of x is just b times L, that limit without the b there. The sum or difference, I can add or subtract those limits together. The product, I can multiply my limits together. Quotient, I can divide my limits as long as the denominator is not 0. And the power rule, if I know the limit as x approaches c of f of x, then if f of x is raised to a power, I just take the limit to the power. So let's look at this. The limit as x approaches 2 of 4x squared plus 3. Well, those rules tell me that I can separate this into 2. I can make it the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. This also brings in that constant rule. I have 4 times x squared. Well, I know if the limit as x approaches 2 of x squared, I can just plug in 2 squared gives me 4. So this limit actually gives me 4 times that limit, which is 4. And the limit as x approaches 2 of 3 is just 3. So now I have 16 plus 3, which is 19 for my limit. We also have limits of polynomial and rational functions. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x equals p of c. That just means that in any polynomial, you can use direct substitution. If r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of x is not 0, then the limit as x approaches c of r of x equals r of c, which is p of c over q of c. Basically, in a rational function, as long as it won't make the denominator 0, you can use direct substitution. So I have a rational function here. I noticed that plugging 1 in for x will not make the denominator 0, so I can use direct substitution. I'll take 1 squared plus 1 plus 2 over 1 plus 1, which gives me 4 over 2, so my limit is 2. The limit of a function involving a radical. Let n be a positive integer. The limit below is valid for all c when n is odd, and it's valid for c greater than 0 when n is even. So if you have a root, the nth root, the limit as x approaches c of the nth root of x equals the nth root of c. You can use direct substitution. If n is odd, you can use it for any value. If n is even, then you can use it for any positive. The limit of a composite function also works that way. If f and g are functions such that the limit as x approaches c of g of x equals L, and the limit as x approaches L of f of x equals f of L, then the limit as x approaches c of f of g of x is f of L. Basically, the plugging in, again, direct substitution. So for A, I have the limit as x approaches 0 of the square root of x squared plus 4. Well, I have a radical. Let's see if I can just use direct substitution. When in doubt, just try it. I have the square root of 0 squared plus 4, which would be the square root of just 4, which is 2. So that one worked. There's my answer. For the second one here, let's try direct substitution. The cube root of 2 times 3 squared minus 10. Well, 2 times 3 squared, that's 2 times 9, that's 18, minus 10. I get the cube root of 8, which is also 2. Both of those limits equal 2. Limits of trig functions. As long as c is a real number in the domain of the given trig function. If c is not in the domain, this is not true. But basically this just says that as long as c is in the domain of my trig function, all trig functions can be evaluated, the limits of all trig functions can be evaluated using direct substitution. So the limit as x approaches 0 of the tangent of x. I should be able to just plug this in and say that is equal to the tangent of 0, which is 0. The limit as x approaches pi of pi cosine of x. I should be able to substitute and say pi times the cosine of pi. Well, the cosine of pi is negative 1, so my answer is negative pi. And the limit as x approaches 0 of sine squared of x. Well, I know the sine of 0, and then I'll just square that. The sine of 0 is 0, and 0 squared is still 0. Then we have functions that agree at all but one point. If c is a real number, and let f of x equal g of x for all x not equal to c in an open interval containing c. If the limit of g of x as x approaches c exists, then the limit of f of x also exists, and limit as x approaches c of f of x is equal to the limit as x approaches c of g of x. Let me give you an example for this one. If f of x equals x plus 1 times x minus 7 over x plus 1. Well, I know this function does not exist at x equals negative 1. But I also know that I could have canceled those two and been left with just x minus 7. This is saying that the limit as x approaches negative 1 of f of x, since I can simplify this to get g of x, those limits will be equal. And with g of x, I can just plug that in and get negative 8. So I know the limit of both functions as x approaches negative 1 is negative 8. So this brings us back to our problem from earlier. If I try to just direct substitute, I get 0 over 0. We actually call that the indeterminate form, which is a no-no. So I factor. So this will equal the limit as x approaches 1. Difference of cubes, we do x minus 1 times x squared plus x plus 1 over x minus 1. Those x minus 1's cancel, giving me the limit as x approaches 1 of x squared plus x plus 1. Now I can just plug in the 1. I get 1 squared plus 1 plus 1. My limit equals 3. Now we have some strategies for finding limits. Learn to recognize which limits can be evaluated by direct substitution. Honestly, when in doubt, try it first. When the limit of f of x as x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f for all x other than x equals c. Choose g such that the limit of g of x can be evaluated by direct substitution. Then apply theorem 1.7 to conclude analytically that the limits are equal. Basically, simplify your function so that you can just plug it in. And step 3 is just use a graph or table to reinforce your conclusion. A couple other techniques. The dividing out technique involves dividing out common factors. In determinant form, that's an expression such as 0 over 0 that does not allow you to determine the limit. 0 over 0, not allowed. Same thing as infinity over infinity, also not allowed. And then there's the rationalizing technique that involves rationalizing the numerator of a fractional expression. Multiply the numerator and denominator by the conjugate of the numerator. These are just tips and tricks to help us, and we'll look at them a little bit more closely. So this first one, I always would go for direct substitution right away. If I plug in negative 3 to the numerator, I get 9 minus 3 minus 6, which is 0, over negative 3 plus 3 is 0. That's a no-no. That's your indeterminate form. You don't want 0 over 0. So instead, we'll try to factor the numerator. If I can factor it and simplify, then I'm in business. I can factor this to x plus 3 times x minus 2 over x plus 3. Those x plus 3's cancel, leaving me the limit as x approaches negative 3 of x minus 2. And now I can just plug in negative 3, and my limit equals negative 5. So I would say the limit as x approaches negative 3 of this whole function equals negative 5. All right, this is a case where the rationalizing method will be used. So I start off by trying to plug it in. If I plug in 0 in the numerator, I get 0. 0 in the denominator, I get 0. That's indeterminate. All right, this is the rationalizing technique. So I take my original expression, and we are actually going to multiply the numerator and denominator by the same thing. And that same thing is going to be x plus 1, the square root of x plus 1 plus 1. When I multiply my numerator, let's see, limit as x approaches 0, I get x plus 1 minus 1 over x times the square root of x plus 1 plus 1. Now I see if I can plug in 0. I still can't, because I need to simplify further. The limit as x approaches 0 of x over x times the square root of x plus 1 plus 1. I notice my x's cancel. Remember, they leave me a 1 in the numerator. The limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now if I plug in 0, I get 1 over 2. And there's my limit. So the limit as x approaches 0 of this whole crazy original expression equals 1/2. And now that brings us to something called the squeeze theorem. The squeeze theorem basically says that f of x is between two functions, h of x and g of x, for all x in an open interval containing c, except possibly at c itself. So basically I'm telling you, f of x is in between h and g in this interval. If the limit as the limit as x approaches c of h of x is equal to L, and that's also the limit as x approaches c of g of x, then if I squeeze my function in between those two, well then there's nowhere else for it to be except L. And then we have two special trig limit. The limit as x approaches 0 of the sine of x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. So let's use some important pieces. Let's rewrite this expression, because I don't know. Tangent of 0 is 0 over 0. We'd get 0 over 0, which is indeterminate. So instead, let's rewrite it. Tangent of x, well, that's sine over cosine. Divided by x. And let's actually make that sine of x over cosine of x times 1 over x. Well, we just had a special limit that sine of x over x is equal to 1 when the x approaches 0. So let's rewrite this as the limit as x approaches 0 of sine of x over x times 1 over cosine of x. Because then I can split it into two pieces. The limit as x approaches 0 of the sine of x over x times the limit as x approaches 0 of 1 over the cosine of x. Well, as x approaches 0 of sine of x over x, we know that should be 1. And as x approaches 0 of 1 over cosine of x is also 1. So that means my answer is 1. So the limit as x approaches 0 of the tangent of x over x is equal to 1. And now it's time to practice.